Thank you. Thanks a lot for the invitation. So as you can already guess, and you will see during the talk, this falls slightly outside of the main topics of this program. And so I think any other week I would probably have talk more about modular Higgs bundles and motifs of modular Higgs bundles and mirror symmetry aspects. Dear to Michael. But since this week and next week there will be a lot of singularity and like refined invariance of singularity. I thought that as a non-expert in singularity theory, I would talk about this topic, which is about relatively fine, I hope interesting invariance of singularities. So maybe the first sign that this is a bit outside of the topic is I'm going to fix a base field, and I'm not going to assume that it's algebraically closed, and certainly not that it's a complex numbers. The only restriction that I'm going to make is the characteristic of K is not 2. So why do I do this? Well, these invariants, as I will explain in a second, there will be quadratic forms. Actually symmetric bilinear forms, but I'm making this assumption as kind of a basic hygiene when working with this object. I mean, the theory in characteristic 2 is also interesting, and there are things that one could say about the question that I'm going to talk about in characteristic 2, but it's all as a word. Okay, so the first thing I'm going to tell you about is let's say something, some more introduction. So these invariants, they sort of fit into a larger picture which has emerged in the last few years of the quadratic and numeratic geometry. And so it actually has come out as a development out of motivic homotopy theory, so which is somehow where I come from. And I like to say that it's a kind of applied motivic homotopy theory. And certainly some of the most concrete invariants that you can get out of this rather abstract theory. But in some sense, it's not even the right characterization, because as you will see, you can define and work with these invariants without really talking about motivic homotopy theory. And many of these invariants could have been defined many years ago, well before the definition of the motivic homotopy category. And actually, I'm going to try to convince you of that by showing you how certain quadratic forms come out of coherent duality. And this will be somehow where these invariants really come from, geometry. Quadratic forms from. But to do that, I kind of have to have a place to put my invariants. And so this is going to be a very simple case of Hermitian case theory, or also known as Grothendieck-Witt rings. All right, so as Emily Cliff said in a talk at the beginning of this program, so recall or learn really quickly the following definition. So the Grothendieck-Witt ring of K, so is going to be a group completion of a monoid, and in fact of a semi-ring, so that's why it's a ring. And what is that ring? So it's I take the isomorphism classes of so finite dimensional non-degenerate symmetric bilinear forms. So on K vector spaces. And because I made this assumption, I have the right, and I will abuse that right to call this a quadratic form. So every time I say quadratic form, it's assumed to be finite dimensional non-degenerate. This has a natural operation of direct sums, or orthogonal direct sum, and a tensor product. And so if I take the group completion of this, I get a ring. So as the definition suggests, it's a kind of case, and also the name of the section, it's a kind of case-theoretic invariant. If you do this without the form, you get the K0 of the base field of K, which is just the integers. What happens in this context, in this Hermitian case theory context, is that already for a field and in degree 0, you get something quite interesting. So let me show you that this can be interesting. Yeah, so first a bit of notation. So I will write this for the, and which, so it will be the sum of the individual thing. This is the class of the diagonal form. So a simple fact which comes from the fact that every quadratic form can be diagonalized is that this has a presentation. So these are because I assume non-degenerate, these are invertible. Modulo 3 relations. 1 is equal to 1. And A plus B is and again, so here A, B, and here A plus B are assumed to be non-zero. So this is a kind of deceptively simple statement, because of course it's a very simple presentation, but it's actually the resulting ring really depends on some of the arithmetic of K in a complicated way. So let's take an example. So certainly as examples, and at the same time I will introduce some invariants which are useful. So there's always a rank function, right, which goes to this, and I mean you should think of this is the map back down to K series, and for this is an ISO for K algebraically, or indeed quadratically closed. So whenever every element is a square. Let's do K equal to R. Then, so by guess the theorem of due to Sylvester, so we know what quadratic forms of R look like, and in this language, it's and here, so I'm going to introduce it's a good opportunity to introduce a particular class, so that I will denote H, which is a class 1 minus 1. So this is the hyperbolic form. So hyperbolic forms are somehow the trivial part of the ring, and indeed you can show that Q times H is rank of Q times H. So somehow it's it absorbs everything. So we're usually interested in some of the non-hyperbolic contributions. And this is roughly speaking by the, I mean, you have to tweak the formula, but this is roughly speaking by the given and by, I guess I could give you the formula. So the class of the form phi is sent to the signature of phi plus, and so that's also the opportunity to introduce signature over R, which of course is the other invariant. The Grothendieck Witt group of a finite field. So here Q is an odd is a power of an odd prime. This is I guess this is 2 epsilon square, and this is given by class of phi goes to rank of phi plus epsilon, the discriminant of phi. And so that's, again, an opportunity to introduce a new invariant, which makes sense in general. So the discriminant of phi is the determinant of the matrix, so of any matrix representing this form, and this lives in the square classes. Okay, so for local rings, and well, let's say for instance for Q and for in general for global field, one needs one more invariant than this, which is like the Clifford algebra, somehow to get a complete set of invariants for quadratic form. And somehow writing down the GW for number field, it's basically a part of class field theory. So there's already quite a bit of information there. And then for general K, so we know, thanks to the Miller conjecture, so proven by Vygotsky, that this thing contains a lot of information about the Galois homology of K. So okay, so that's all I want to say. Now I'm going to give you some examples. I mean, how to and so I'm going to define the quadratic Euler characteristic. And so I'm going to start with in the smooth projective case, but the singularities will come later. Then we can look at the Hodge homology groups in sort of complementary degree and degree of the forms. So by cup product, this maps to Hn x omega n, and then by the trace map in from Serreduality, this maps down to and this induces quadratic form on the direct sum of the, so that I will call the Qx on the sum of the Hodge homology, and it's actually better to think. I mean, I got two, and I put this in. Somehow, if I put this in degree Q minus P, and so yeah, I guess what I want to say is that, of course, here by definition, I have classes associated to bilinear form on vector spaces. But in fact, if I take any bounded complex of K vector spaces with some pairing, I get a class in this ring. So I think of it in this way. Here as a complex with trivial homology. And so by definition, the Euler characteristic, and so in this talk, it will have no decoration because it's the main. It's the main player, but yeah, it's just the class of this in the cosine tree. So here are some properties of this construction. First of all, if n is odd, then as you see, somehow you only pair up two different. I mean, there's no form on any single Hodge homology. They always pair up 2 by 2, and that implies immediately that the form is hyperbolic. And in fact, and sorry, actually maybe it's better to start with property 0. Somehow the rank of this is the topological Euler characteristic, which you can define. I mean, if you're over C, or if you have a complex embedding, you can define it as the Euler characteristic of the complex point, but you can also define it in general using L-adic homology. So yeah, then this is the topological one divided by 2, which in this case it has to be even times h. And in general, if n is equal to 2D, then the same argument shows that this is, in fact, the class of a form on HD omega d. So there's only one group where you get a non-trivial, a non-hyperbolic form, let's say, plus some hyperbolic form. So at least in this smooth projective case, it's all about even dimensional varieties. So if k is equal to r, then the signature of this turns out to be the topological Euler characteristic of the real points. Okay. And so this is kind of typical of this general subject of quadratic enumerative geometry. That is that when you do it over R, you get invariants which, if you use the rank, sort of give you the complex picture, and if you use the signature, give you the real picture. Yeah, and in general, so if you fix, if you take the discriminant of the quadratic Euler characteristic, so which again lives in. This is equivalent in the sense that I'm not going to make precise by a theorem of Takeshi Saito to the information contained in the determinant of the l-adic cohomology of X over any algebraic closure and for any prime L prime to the characteristic. So as a Galois representation. So somehow you can show that in this Galois representation is up to a tight twist of quadratic character, and it's this quadratic. So I would say that actually, so this is all that we know in general, in some sense, about the arithmetic meaning of this invariant, and it's a bit of an unsatisfactory situation. But for instance, there's a conjecture of Saito which predicts what gives an interpretation, again, a kind of l-adic interpretation of the Clifford invariant. So there's probably more to be done in that direction. Okay, so I want to talk about singularities. So here's the theorem. I'll make it. So chi, and it's not my theorem. It's just one. That's very cool. Yeah. One. Yeah. This one. So H is this hyperbolic form, which is rank 2. It's a defined always. Oh yeah, sorry. I mean, I sort of use this to introduce various sort of concepts which make sense always. The only thing that doesn't make sense in general is like the signature, which requires a real embedding. Okay, so the proposition is that this chi extends, which I just defined on smooth projective variety, extends to a ring homomorphism, which I will denote by KC because outside of the world of smooth, outside the world of projective variety is really a compactly supported. Okay? From the K0 varieties, GW. So let's start with the proof in characteristic, a simple proof in characteristic 0, which is really the main. I mean, yeah, many of the results will actually be in characteristic 0, but so the idea is to use the presentation of K0 variety due to Francesca Bittner. So now Francesca, I got. So then we, I mean, the generators here are smooth projective varieties. So, and we know what to do with them. And then there's a blow up formula, and so you have to prove the blow up. This satisfies the blow up formula. And in fact, since you're in characteristic 0, you, I mean, you can use the Durham cohomology instead of the cohomology to define this pairing, and then it's really like blow up formula for algebraic Durham cohomology. Plus some compatibility with duality, which is not. Yeah. it's whatever it's whatever it is to, yeah, it's some, yeah. Maybe I should have the congruent to H. Okay, so so this is a simple definition of this invariant, and so now it makes sense for any variety in characteristic 0. And in some sense, the question of the main question of this talk is, can we compute it in some interesting examples for singular variety? But I'm going to say a little bit about another definition in that works in characteristic P, but I'm going to be quite. And this is the part with the motivic homotopy theory. But it will let me introduce a very nice definition, which if you haven't seen, it's very useful. And so if you have a symmetric monoidal category, you see that an object X in C is dualizable if there exists a dual and maps. So an evaluation map from X, dual tensor X to the unit object, and a co-evaluation map such that you have a triangle identity. Somehow if you use these two maps to define something like this in the only way that makes sense, this composition is the identity of X, and then there is just the same one for its dual. And if you have a dualizable object, then so I will write C dual for the subcategory of dualizable objects, and you have an endomorphism. Let's call it of X. Then you can define the trace of X of F, as an endomorphism of X. So it's going to be an endomorphism of the unit object in C, and it's defined just using these ingredients. And there's basically again one definition that makes sense. Use the co-evaluation. I guess there are several definitions, but they give the same thing. Then you use F tensor identity. Then you exchange the factors, and that's why you need the symmetric monoidal. And then you evaluate. So this seems a bit abstract, but it recovers basically, a lot of standard definitions. So for instance, if let's just take some complex of just a bounded complex of vector spaces, right? So an object in the DRS category. So clearly, the endomorphism of the unit object, which is k in degree 0, this is just this is just k. But the trace this is just going to be the usual Euler characteristic. Sorry, the usual sum of the traces. So I'm getting a bit ahead of myself here. It's the no, sorry. So in this case, it's just in K. Right? But in particular, if I take the trace of the identity, then I get the usual Euler characteristic. So okay. So what? Yeah. What? Okay. So a more topological example, right? If X is a finite CW complex, and here we need a bit more technology, but it's somehow what's going to happen also in the motivic case. So I just do it. So you can form, you can go into the world of algebraic topology and more specifically a stable homotopy theory. And so you can form the infinite suspension spectrum of this, which lives in the stable homotopy category, the topological one. And this object will be dualizable. So what are the endomorphisms of ones? I mean, one here is the sphere spectrum. And so this is, by definition, is the stable pi zero of the sphere spectrum, which by the theorem of Serre on like pi n of Sn, this is just set. And the trace, let's say just the trace of, let's just talk about the trace of the identity. For the trace of the identity is the topological Euler characteristic of X. And if F was an endomorphism, for instance, if F was a continuous self map, the trace of F would be a definition of the Lefschetz number. Okay, so now we go to the motivic world, and so I'm going to just introduce briefly, not really introduce, just mention briefly this category. So this is the stable motivic homotopy category, which has been introduced by Morel and Voevodsky. So if you don't know what this is, you should think of this as either SH but four K varieties. So now it's a kind of homotopy theory, but built out of K varieties, and where you replace the usual homotopy by plus A1 homotopy. Or it's an homotopical variant, or variant of categories of motifs. So it is, in some sense, two certain homotopical invariants what motifs are to things like Chow groups and motivic cohomology. Okay, now you might see where I'm going. Yeah. Yeah. Yes. Yes. Yeah. And the thing, so yeah, maybe I should have said is that for smooth projective varieties, I don't have a formula. I don't have a sort of theoretic formula. The best I have is the one that I'm going to, in general, is the one that I'm going to state now. So I'm just going to state a combination of a few theorems, which, and then you will see what. So as a result of Ayub and Ryu, so if you have any variety, and here I'm just going to introduce a slightly non-standard notation, but I'm just going to say the motif with compact support of X, which in this category SH, in SH of K is dualizable, and here I'm lying a little bit in positive characteristic. I have to invert P, but that won't matter at all. Then there's the theorem of Morel, which will tell me where these which will tell me where these traces are going to live, because the endomorphism of the unit object in SHK, so the motivic sphere spectrum, this is now a GW of K. Somehow this is where this is one place where quadratic forms sort of enter unavoidably when you start doing stable motivic homotopy theory. And now I can state a formula, so which is due to Levine and Raxit, which is that if X is smooth and projective, then the trace on this motif with compact support, but which for S smooth projective is without compact support as well, is this quadratic Euler characteristic. And as you can imagine, when you come from motivic homotopy theory, you see things a little differently. You actually define in general this quadratic Euler characteristic by this, and then what they prove, and that's how they saw what they prove. So they write it. You prove that for a smooth projective variety, it's given by this form of homology. And so using this, you can also you get an extension as well of KC. And that also tells you, in some sense, what these, that gives you a more conceptual explanation of what this thing is. Yeah, so as I said, the question is, can we compute these things for singular varieties? And yeah, unfortunately, there isn't until now really I mean, it's not like for a singular variety we can form some kind of finite dimensional cohomology carrying a natural form, which with class gives this, as far as I know. I mean, that would be good. So all the approaches are kind of by resolutions or by smoothing, so we'll see some examples. Okay, so but then before I do that, I'll just define another sort of geometric source of these forms, just to see that in the singular case you still have some interesting things happening. So I'm going to take a smooth variety and a function, and I'm going to take so with an isolated critical point at x, which for simplicity I'm going to assume is a rational point, but yeah, you can do with that. So if so you can make a much more intrinsic definition of what I'm going to make, but let's just jump through some local parameters. And then you can define in this context a very classical object, which is the Jacobian ring of f at P, the quotient of the local ring at P divided by the partial derivatives of f, the ideal generated by the partial derivative. So this, by the assumption that this is an isolated critical point, it's a finite dimensional K-algebra. And I claim that it carries a natural quadratic form. And well, first of all, why is this interesting? So classically, one reason that it's interesting is that it's its dimension, which is the depending. Let's just define this to be the dimension of this. So this is the Milnor number, and it is known in this case that this is related, let's say, over the complex numbers to the number of vanishing cycles of the Milnor fiber. So I'm going to say that there is sort of an algebraic structure behind this. Yeah, okay. So the point is that it's and I don't want to go through the full story here, but basically you can do Grothendieck duality. You can do duality, and you can use Grothendieck duality for this ideal to define a quadratic form on this thing. And concretely, it works like this. So there's a distinguished element that will just denote by E in the that's capital E in this ring, and in characteristic 0 you can actually define this. I mean, this is slightly, yeah, you have to interpret the formula carefully, but first of all you have to be in sufficiently large characteristics so that you can divide by the dimension, and then you put the determinant of the S-chain. And then you take, so pick any linear form, let's say, on. And the fact that we're picking, the fact that we're making all these choices is just because we are taking some intrinsic construction coming from really Grothendieck duality, and we're sort of writing it in a more concrete way, but then you have to make choices. You take any linear forms that with lambda of E is equal to 1. And then you define, maybe I'll go. No, okay, I'll finish it. Yes. Sorry.
Sorry.
Yeah. Yeah, so and so then, yeah, the claim, and this is not completely trivial in positive characteristic. I think it's due to Schecher and Stoch in general, is that this carries a quadratic form, and which is defined as follows: xy is sent to lambda xy. So the claim is that this is non-degenerate. And so by definition, the quadratic Miller number, which I'm going to give it a little operation here, it's the class of this. QFP in the Groton digits. Okay, so so one advantage of this is that it's much more computable, right? Than Hodge cohomology of a smooth projective variety. It's given to you as a kind of finite dimensional thing, and so you can compute this quite explicitly in any given example. And one thing that we did with Marc, Levine, and Srinivas is to apply this to the computation of the Euler characteristic of a smooth projective hypersurface. So yeah, roughly speaking, what you do is you take you take your x here is an plus 2, and you assume that f is homogeneous of degree d, so prime to the characteristic. This is basically the only statement that I will write, which is really not in characteristic 0. So. And plus you assume that v, let's call it y, which is v of f, instead of pn plus 1, is smooth. Then so we have it's just writing any smooth projective. It's just a way to talk about any smooth hypersurface. And then so the theorem is that then the quadratic Euler characteristic of this hypersurface is the class of d plus minus d times this quadratic Milnor number plus some number of thing which you can, yeah, because we know that the Euler characteristic of a topological one you can work out, but it's not very enlightening formula. Yeah. Oh yeah, sorry. Yeah, P. Yeah, I think P is equal, or rather, X is P because I use P everywhere. Okay, and yeah. So and this is something that you can really, for instance, for diagonal hypersurfaces, you can write down an explicit formula. So the proof of this is an application of the method of Griffiths to compute the Hodge cohomology of smooth projective hypersurfaces using residues on the open thing, and result of Carson and Griffiths, which give you some control on the cup product, and then like careful bookkeeping to get to the right formula. And we also did a version for weighted projective space. And some, yeah. Okay. So then there is also an important construction, but I don't want to say too much about it, which just to this is to enlarge a bit the focus and show you what this quadratic enumerative geometry is really about, which is, I mean, what I've been doing is mostly Euler characteristic, but I think it's fair to say that it's mostly about Euler classes. So if you have a smooth variety and V a vector bundle of rank D equal to dimension of X. And let's also, yeah, okay. Then there's an Euler class. I'm just going, okay, maybe I'll put a decoration so it's not too confusing. So now, but now this is not a class, of course, over the base field. So it lives over a similar group, so which is not a ring in general, which first of all, yeah, takes lives on X, and then it's somehow twisted by a line bundle, in fact, by a shifted line bundle. So what is this group? Well, it's defined in a very similar way to over a field, except that now you're going to take vector bundle and maybe perhaps even better like perfect complexes over X together with a symmetric bilinear form, but which symmetric bilinear form is valued in this shifted line bundle. Then that's what it is. And this is defined in terms of a sort of explicit causal complex construction for any section, and that's sort of where I'm going now. So if S is a section, then this class sort of localizes on the zero locus of S, and so you get a class. And of course, again, now you have to start thinking about what this group with supports are and so on, but sort of the usual game with cohomology series. And when S has isolated zeros, then in fact, this splits as a sum of local contribution, and the local contribution are basically of this form. There are also forms on finite dimensional algebras which are not necessarily Jacobian. I mean, yeah, basically the Jacobian algebra of the section. So S isolated zeros, then you get local contribution. And I'm just going to write it's of Milnor type. Okay, and then another thing that you can do with Euler classes, and that's going to come later, so I'll try it now, is you can then try to push them forward to the base. And in fact, this is how this theorem of Levine and Raxi that I'm going to erase. So I should have said that they call this a Gauss-Bonnet formula, and it's formally very parallel to like the Chan-Gauss-Bonnet theorem. It's about the push forward of an Euler class. Yeah, exactly. Okay, so now I'm going to talk about a specific case, which is the case of symmetric powers and Hilbert schemes. So, and yeah, although one can think a little bit and do a bit better, I'm just going to assume characteristic 0. And so I'm going to take, so X, just X with projective. And so the question is, what is the other characteristic of the symmetric powers of X? So, of course, for the topological Euler characteristic, we know we have McDonald's formula, and so which shows that these Euler characteristics are determined by the Euler characteristic of X, and that's the kind of thing that we want. So the answer in general is more complicated, and I wish I had a sort of general thing to tell you, but but the answers that I know are expressed in terms of the following construction. So let's say that I have a quadratic form. Then I can form, and here I'm also using that, characteristic 0. I mean, in general, there's another construct, sort of alternative construction. Going to define this form. So this will be a form on the sim NV, and it's going to by definition, this is the permanent of the matrix. So the determinant without the sign. So so in positive characteristic, this tends to be degenerate, but in characteristic it is non-degenerate. And so okay. So here's a very easy case. So the case of, just to fix ideas. So the case of a smooth projective and a geometrically connected curve. Then the other characteristic of this, which maybe I should have been, I mean, you all know the notation. This is just Sn of chi. And this is the direct application of this Levine-Raxit formula. But actually, the geometrically connected restriction is kind of interesting because even if X is a zero-dimensional variety, so is a field extension, like the induced form on, like the symmetric power of the trace form of like a separable field extension is kind of a complicated object, and it's been studied a lot in number theory. And it's not so clear how to mix up the geometrically connected case and the field extension. Okay, so here's the main term of this part. So this is joint work with Lenny Taelman. So here X is the smooth projective geometrically connected surface. And so the result is that this quadratic Euler characteristic. And here it's a little unsatisfactory. It's this plus lower order correction. And I don't really have a good, I mean, I can write some formulas, but they are ugly. And I'm just going to show you some simple formulas. And also the proof will show you where they come from. So here's an example. Chi of X, the second symmetric power. I mean, this is just this. I'm just going to write chi for the chi of X. I just write maybe 1 as a one chi of X4. So basically, you have always this kind of very simple rank 0 form, like difference of two integers, and then things which are parameterized by partitions of, and for every partition. So let's see what I want to say about the proof. So as you can guess, if you've seen this object at all, we're going to use the Hilbert scheme of points. Because this is smooth projective, and so we can apply Gauss-Bonnet to it. So this so xn to xn is a resolution of singularities whose geometry is very well understood. And so for xn, we also have so and in this case, let's just talk about the Doran cohomology of the Hilbert scheme. So as an explicit basis in terms of Nakajima operators. And so even though actually the multiplicative structure on this is complicated, I mean, there's a lot is known about it, but the answer is complicated. The form that you get by cup product plus trace is actually very simple. And in some sense, it's part of the very foundation of the proof, that because it's this adjunction between annihilation and creation operators. And so for this, you get from this, so you just have to look carefully at the formula, get a formula for this form. And so you get a formula for the other characteristic of the Hilbert scheme. And let me just write it. So, and this is where the theory sort of diverges a little bit from the classical story, which is that there are some factors which sort of make the formula complicated. So it's indexed by partition. And then to conclude the proof, you compare this with a formula of the targeture in the K0 of varieties. So the original paper is written for K algebraically closed, but we went carefully through the proof, and it seems to work for K when K is not algebraically closed. So it's a formula in the K0 variety, and so it implies a formula for this other characteristic, which doesn't, I mean, which is formally similar but doesn't have these corrections. Okay, and just to make sure that we didn't make a mistake, we checked some of the concrete consequence of this formula for discriminants, and it seems to match. At least certainly the naive formula that certainly doesn't work. Okay, so I should mention that there's also been work so in a different direction, not directly computing this thing, but trying to prove an analog of the Yau-Zaslow formula by Pajwani and Pal. So they get some partial result towards I mean, they prove a version of this formula in a quotient of the quotient division. Okay, so I'm running out of time. I'll just say a little bit about conductor formulas, which is really was really my starting point of my interest in this. I don't know, it should be. And okay, maybe I should say that I expect that there will be a much better answer to this. And when preparing this talk, I have some ideas to go beyond this case of self-proof. It's not ready for public consumption. So yeah, quadratic conductor formula. So here the setup is X is smooth. So again, characteristic of K is 0. X smooth of dimension n+1. And we have some F. Yeah, okay, maybe to make my life easier, I'm going to have a more general setup. I'm just going to take a function and some, again, some. So critical. No, sorry, what am I doing? No, that's not what I'm. Okay, so the classical conductor formulas in this context. So which goes back for isolated singularities over C to Milnor, and then was sort of extended in many directions by many people, is that the difference between, so the other characteristic, sorry, this should be let's say flat proper. flatness is very important, proper, since in some cases may do better. I mean, for flat morphism, we know that sort of coherent cohomology is the characteristic. Yeah, the other characteristic of coherent cohomology is constant. This is not the case topologically, and so we know that the difference, which can be expressed in terms of vanishing cycle, is this is a sum. I mean, first there's the case in terms of isolated singularities. So this is the Milnor formula that I've already mentioned. And so yeah, by critical point, I mean like critical zeros of these topological Milnor numbers. And then in general, it's the -1 to the n times the degree of a topological an Euler class. And what Euler class is the Euler class of omega 1 x over k localized by the section df. This lives over 0, so can take its degree. I mean, so this is new to Milnor, and this was a conjecture of Bloch, and it was proven by, I think, Kapranov in some sort of hidden version, and yeah. Okay, so now the quadratic setting. So T is my coordinates on okay, so now the first, I mean, if you try to, yeah, let's just try to lift this formula to the quadratic Witring. I want to replace this by Euler characteristic, but the problem is that these don't live in the same ring, so I just make them. There's a specialization morphism which depends on this T, so T. So that now it lives in the Euler characteristic of K. And so I can ask, is this equal to the same formulas but in the quadratic case? So I'll just write, because I'm running out of time, I'll just write quadratic analog. And what do I mean by this? Well, you replace this by the quadratic Milnor number, and you replace this by the quadratic Euler class. And then you have to define what the degree is. So that's the question. So the answer is no. Sorry? Yes, sorry. So SP, so it's the unique ring homomorphism. So from GW of KT to GW of K, which satisfies that SP P of T to the n times U, where U is a unit, so U is so it's in KT localized away from 0. This should be equal to just the class of U bar in the. Okay, so yeah, so the answer is no, and there are some very simple counterexample, and okay, I don't really have time, but even in dimension 0, like relative dimension 0, there are counterexamples. Maybe a small sort of piece of evidence to show that maybe there is something. This is yes for, and this is also due to me and Levine and Srinivas. Yes for K is R and isolated singularities. And there it's a reformulation of classical results about the sort of topology of real singularities of Eisenberg, Levine, and Kim-Schiasvili. Okay, but so I should wrap up. So so yeah, what happened is that I don't know. Initially, I thought that this would be true, and this would somehow be for isolated singularity. This would be relatively easy, but it's really not true. And so with Levine and Srinivas, somehow in the same paper that and that was actually motivated. The computation for hypersurface was motivated by this. We did some very simple. We did explicit formulas for some very simple singularities, basically things that can be resolved, basically like cones over or weighted cones over weighted. Smooth projective weighted hypersurface. But there are some correction terms that we did not understand, and we still, to some extent, do not understand. But so yeah, in joint work in progress with Ran Azouri, Niels Feld, Jonathan Arpaz, and Tassos Moulinos. So we are working on adapting the recent work of Toen and Vezzosi and Beraldo and Pipi, which have had this beautiful idea, but beautiful, but sort of technically difficult to realize idea that such a formulas are actually Gauss-Bonnet formulas themselves, but they are Gauss-Bonnet formulas for a non-commutative space, which is the GG category of matrix factorization of the function f. And their motivation was the mixed characteristic case, because that's the case that's still open here. But for us, already characteristic 0 is plenty. And their proof strategy actually simplifies a bit in characteristic 0. And so we can already do a part of this construction. But maybe I will. Sorry, just remember one more thing, which is so about this. So what this proof strategy suggests is that these correction terms are actually related to the non-unipotent monodromy of on the vanishing cycles. But again, to make this precise, especially in this motivic context where there's actually no honest monodromy operator on SH, on the vanishing cycle in SH, but is tricky. So we kind of expect that this formula holds without corrections in the unipotent case. Yeah. 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 So, but there's a restriction. So, and this is sort of typical of this sort of quadratic theories, like I mentioned, case theory. You cannot always push forward. So what you can do is you can push forward if you have an orientation. And what's an orientation? Yeah. So you see what I mean? Yeah. So the difference between the determinant and the relative canonical thing must be a square of lambda. And then you can push forward and get a degree. No, yeah. If you put if you take canonical boundary fit by this, yeah, and what you can do a little better, which is things that differ to this by a square. And so in general, this kind of thing is, and also the fact that basically there's only an higher class and not higher Chern classes, at least in a discrimination case theory, means that the type, I mean, it's not the case that every sort of enumerative problem as a quadratic lift, but when you can express things in terms of Euler classes, then there will be a quadratic prime.
So only know in the context of is there some
it's the same part of the same story. Yeah.
So there are some mistakes.
I mean, it's a bit. It's the same thing as the same difference as in classical enumerative geometry, where you can either like try to prove like Riemann Roch or type theorem, so which relate the coherent invariant with the topology, which is more what I'm trying to do here. And on the other hand, you can do enumerative geometry like computing intersection numbers, and that's what many people been doing. So it's not things that I've been personally working on, but certainly Marc, Levine, and other people have done some counts, yeah, this kind of pair counting. Yeah. So in these formulas, you can see that those are all positive. So when you go to the real numbers, these actually you get this sort of simple formula, and you recover existing formula. Basically, this McDonald formula for real. I've tried. So far I haven't really managed. Part of the issue is that in this, the quadratic string, there's quite a bit of flexibility. For instance, whenever you have a square, you can cross it out, and so it's not clear what the right form of the formula is. Yeah, but so I've been thinking about more other approaches which would give a more systematic formula, but it's not. Yes. Well, yes. Well, it's the same in the sense that it's the same for smooth reactive variety, but also once you have once you are in this motivic homotopy picture, you can also define a chi without compact support. But then you cannot do this through the K0 variety because it doesn't satisfy. It was more of it was more like a presentation, a choice of presentation, but not starting with the motivic homotopy theory, because if you start with this, you can just define it without compact support. No, they're just chi-C because chi is not additive.
So, like, related to like
symmetric power, I don't know. I asked myself this question this morning when we did the talk, but I haven't thought about it because I didn't know all these results. But yeah, I don't know if. Yeah. A lot of the techniques that we talked about this morning are just not available.